So first of all, thank you everyone here for inviting me and being here with me. So a more honest title for this talk would be something like me and my computer and math. So I'm gonna talk about my personal journey with my computer on how I did mathematics, built my career with it, and along this story, I will talk about experimental mathematics and the recent involvement of AI with it. So I hope you get something that's helpful to you as I talk about my own journey. So let me start. So I will describe like what that means later. Maybe some of you can guess already. When I was a middle school student, I really wanted to become a international mathematical Olympiad contestant. Like for adolescence reasons, I wanted to be great. I wanted to brag to my friends, but I couldn't do it. Like Korea is very competitive here. Like we have like 4 more rounds of like a competition to become a like international Olympiad contestant, and I think I failed at the 3rd one. I really try hard, so it was a little bit sad for me. But along that way, I acquired a certain taste on problems, on mathematical problems. I started to like elegant problems with like simple definitions and simple ideas, which are very hard to find. But once you find the right idea, it solves the problem like a very cool puzzle. So through like mathematical Olympiad experience, I started to gain interest in mathematics and built my like taste on mathematics. And because my IMO like dream failed, I tried the International Olympiad in Informatics one. I thought coding was a little bit easier than math somehow, but no, they are much faster in like programming. Like while I can like prove theorems a little bit faster than them, they're like once they get the right idea, they're like they do this much faster. But so I also couldn't make it. I think I failed the 2nd round, like worse than the 3rd round in IMO, right? But at least I learned how to code. So I have a love for like those like terminal screens and like the codes in it. So so I could not give up. So what I did was to combine the 2 skills that I learned for each attempt and try to build a career out of it. So this was my first theorem in combinatorics that I published with Hayan Nam and Myungjin Yu. And I don't really want to talk about the exact statement, the definitions, etc. But I want to, how do I say, showcase how I combine those 2 skills. And maybe some of you have like a more like a or less similar experience. Maybe you use more advanced programming, etc. But let me talk about like my own experience here. So the problem asks us to basically count a certain type of combinatorial object, number of 2n plus 1, 2n plus 3 core partitions with distinct parts, whatever that means, by a standard like combinatorics argument. In that field, I could reduce it to counting some other type of like a subset of like those points. So here you have a bunch of lattice points, and here the white points are like some certain subsets of the like this thing that I want to count the number of. And the rule is that whenever you have a like white dot, whatever comes like left down, right down should be also white as well. So it's like a downset of this like a Hasse diagram or post-it, if you know what I mean. And another rule is that you cannot like have 2 adjacent number labeled like a dots at the same time. So I can't have like 1 and 2 at the same time. And the whole diagram is made out of like a certain like a combinatorial rule, so that you can see that along this way or that way, they form like a arithmetic progression. So given all this, like basically I want to count some subsets of like this thing with certain properties. And I have to admit that this theorem itself is not new. Someone actually proved it beforehand, but like the challenge was to find the bijective proof. Like the number is like 2 to the power 2n, so it's like very clear. So can you actually identify like the whatever object that you just saw with certain natural object with like exactly that number of like count? So by looking at the diagram itself, it was not so evident. So what I did was to do this. So I really didn't like that the set somehow interfere in the middle. Like it could go up and down in the middle, and the middle part for me, as I thought, was like a bit hard to deal with. So what I did was to just like change the problem, like just remove the middle part completely, and like count the similar subset for this, like this joint subset. So I tried to tackle this problem as a proxy to attack the original problem. And then even after making the problem simpler, like I had zero idea again on how to attack this problem. So what I did was to count the numbers like manually from n equals 1 to 2, 3, etc. But I don't like to compute things with hand. I like to compute things with programming. So one of my favorite languages is Mathematica. So I did the count, and the output was something like this. So you can see that the number goes like 3, 10, 35, whatever. And then there was this question of like what this sequence actually is. So from here, what I will do is to actually copy the sequence and search it through a certain website. So a lot of you maybe already know this website, right? So this is, apologies. This is, so you know, like MacBook and like this is Windows have like different like locations of control button. So like this is where like clutter a little bit. But here we go. Like a lot of like enumerative combinatorists like look up to this site. Like they find some interesting sequence and they want to know if such a sequence already exists in literature. And they go right up to this website called the Online Encyclopedia of Integer Sequences. And if you do the search, you can immediately see that it's a binomial number. So it's a binomial number of like 2 times n plus 1, choose n plus 1. So basically what it does is to count the lattice paths of an n times n plus 1 box going from left corner to right corner, going either upright or downright, right? So up to here, all I did was to compute and like look up. But then, given this as a hint, like I, as an early year graduate student, realized that maybe I can just like combine those two pieces into one. Like you have like a half a piece here, half a piece there, so why don't you just combine those two into one? So I had like a hint. I got a hint out of this like OEIS search, and that's how I found the bijection for the reduced case. So, and then this idea, once I found the right idea, it somehow generalized naturally to the original harder poset as well. So here, what I wanted to convey was that you can essentially work with computers as like a collaborator. And it was even possible back before the emergence of recent LLM AIs. So this is how we proved the following theorem bijectively in the paper. And this idea, I think, I like this quote of Steve Jobs. I would have not liked to work with him, having him as a boss. I think he's brilliant in terms of like intuition. And what he said was that a computer to him was like a bicycle for the mind, so that like we mathematicians like to work with like pen and paper, but a computer can also be your like say like extension of your like mind. So like you can compute things like much further than you could do by hands, and you can also like make abstract ideas like really grabbable by your hand, like if you make the right like setup in your like system. So throughout my whole career, this like bicycle helped me compute and visualize things and make abstract ideas accessible, and in order for me to find the right idea as a human being too. So this was, so with this like early year success, I tackled onto a harder problem. So I wanted to solve an Erdős problem one day, but I still can't. I haven't done like solving any of the Erdős problem yet. But I did really want to solve a like an open problem, which is like simple and elegant, but very like hard. So I learned the internet, like searching to as much problems as possible. Then I encountered a problem on a blog that I liked. This is exactly the blog, and here the post describes the moving sofa problem. The problem goes like, you have a hallway of like width 1 that goes right angle like this. And the task is to find the largest area two-dimensional shape that can move only through like rigid body motions, so that it can go through like this side of the hallway through to that side of the hallway freely. And this is something called Hammersley sofa that you're seeing there. And well, I solved it. So the guy is like, yeah, he mentions me in 2024 update. So, so this was the problem, the moving sofa problem. What is the largest area of a connected shape that can go through this L-shaped hallway? And the conjecture was that this sofa consists of 18 different segments. So this is called Gerver sofa. This shape was conjectured by Gerver to attain the optimum area. And he made this shape by connecting 18 different segments. So here, those 3 have like a horizontal straight lines. Those little ticks, those like tiny little like curved segments between those 2 tiny gap between the ticks are like circles of radius 1/2. And the rest of the curves are like harder to describe. So it is very complicated. So it's interesting why like this particular shape should attain the global maximum. And Gerver's idea was that he derived this like shape by certain type of like local optimality argument, but he also had to like include some like heuristics and assumptions, reasonable assumptions to actually derive the shape as well. So it was not like completely proved that this shape should be the global optimum. So I decided to tackle that problem. I really wanted to solve a open problem and be a mathematician. So what Gerver already knew, and all the mathematicians worked on this problem after Gerver knew, was that by changing perspective, a sofa is essentially the intersection of all the rotating hallways. Like instead of like fixing the hallway and like moving the sofa, you follow the your head around the sofa, and then the hallway like rotates and moves. And the sofa is the intersection of rotating hallways. So the first question to me was, so I kind of wanted to bet my graduate years on some open problem. And one of my first questions was, is this the real like optimum sofa? Like if I were to bet like years on this problem, then I realized that Gerver sofa is not optimum, then like it's very risky, right? So what I did was to make this, so this is a like demo that I made later, like yesterday actually. But I did a similar thing back in the days, like 5 years ago-ish. So what I did was to randomly like position like hallways and like do something called gradient descent. Like I just, like move the like hallway position slightly in the increasing like area direction so that the whole area goes only the increasing direction. And let me try to do that here. So I initially started with a like half circle, which is the intersection of rotating hallways with like inner corner fixed as a center. And then it converges to the optimum sofa, which is curve. So from this, I kind of saw that like as everything converges naturally to curve sofa, it seems to be the right answer. And let me try to do more perturbation here. So like as I click perturb more, it becomes almost like a nonsense shape, right? But if I click optimize, it jumps right back to curve sofa. So this kind of told me that it's somehow like convex optimization. It's not exactly like a convex functional, I think, but like a convex optimization problem, you have only one global like maxima, and like no matter which direction you go, as long as you go in upward direction, you converge to the global optimum. That's kind of the intuition that I got from doing this experiment. And so now that I believe that curve sofa is optimum, is it called pipe dream? Like you have to kind of like hallucinate a bit in order to tackle a hard problem. So like my dream was to use a computer to enumerate all possible different combinations of curves and like just enumerate all of them and like solve the moving sofa problem. But I couldn't get it to work. Why? Because we knew, Professor Joseph Gerber already knew that the optimum shapes should have like 18 different pieces, but like no one could show, no one to cap the upper bound of the number of curves to like even like 10 to the power of 10. Like the number of curves that you have to use were unbounded. So that was a like first challenge that I need to tackle in order to like reduce the problem of infinite search to a finite search. Then I read the work of IMU-KIAS and Dan Romick. They showed that the area of a moving sofa, they didn't solve the optimum bound, but they showed an upper bound of 2.37, which drastically improved the upper bound of Hammersley back in 1970s, I guess. And what they did was also a computer-assisted proof. And as I looked at their paper, their main theorem was this. So in the end, what they did was to write a program that when run indefinitely, so instead of just like asking what is the maximum area of a sofa, you ask, you first define the space of all possible sofa shapes. So we have the sofa shape, and on top of that, you have the area functional. Like area function is simple, you just like compute the area of each sofa. And let's say that you have this diagram as a proxy. Definitely, the space of sofas is not one-dimensional, right? But like let's just draw it as one-dimensional axis. Then the area would look like this. What they did was to devise a software program that could cut the sofa space into like different pieces, finite pieces, and have like a upper and lower bound boxes around them. And as they like progress their program more and more, they cut the pieces into like smaller pieces and have a more refined like upper and lower bound, like here and there. And in this diagram, like as we cut more and more, the upper and lower bound like it does converge to the actual graph. And let's say that this is curve sofa. Then what this tells us is that if the Gerber sofa is the unique optimum, then which we kind of verify, like experimentally verify, if this was the unique optimum, like if we run their like software in a finite time, practically it should be bazillion years. But once we do that, this will like we can at least cut out like all the rest of the like candidates, like for maximality. Like this point should be removed at some point because like this sofa is like inferior to Gerber sofa in terms of area, and you would have like a slightly larger upper bound, which is strictly less than Gerber sofa. So as you like refine the upper and lower bound more and more, like the candidates of maximum area sofa should get smaller and smaller until you reach this portion. So at this point, I realized that the real theoretical or harsh, like theoretical hard part that I need to focus is all the sofas like close to Gerber sofa. And from here, I did another experiment. So this is the Gerber sofa, actually a polygon approximated version. And what I did, so you can see that Gerber sofa has like 3 parts. It has the inner corner of the moving hallway as center, like this, depicted like green. And you have the left portion cut out by left part of the inner wall that makes a convex curve like this. And people call this envelope, I think. You have a bunch of like lines moving and then like, yeah. And this like red line envelope cuts out the left portion. And the same goes for right side here. So remember that the hard part for the moving sofa problem was that there is the number of types of curves was unbounded. Like the number of curves were unbounded. But if we could assume that we could only focus on like sofas that's very close to Gerber sofa, let me try to perturb this thing a little bit. I perturb it very slightly. And you can see that still you have some, like, the envelope is very jaggy right now. It's not differentiable anymore. But you can still see that the envelope still exists. And it's like blue color on the right side. And the middle part is like a green, the left part is red. Even if I perturb a little bit more, it stays the same way. So given all this information, what I knew was that, okay, in theory, I can run Raman College software as long as I can. Then like I cut down the candidates to a small neighborhood near Gerber sofa. Then on top of that, I can just assume that every sofa candidate, I have like left, center, and right part fixed in terms of formula. And on top of that, I also could verify through this experiment that the center curve, the green one, doesn't self-intersect. So I can use Green's theorem to calculate the area function. And finally, that the left and right envelope intersects the center curve transversely, like this, here. So all these observations and like further ideations and experimentations, so it goes like back and forth. Like you try to come up with like right experiment, you see the result, then you come up with new ideas, and then you find the next right like experimentation, go back and forth. And then like this is basically how I solve a geometric optimization problem. So, well, now I am here, I guess, for solving the moving sofa problem. So I want to thank KIAS again for that. And given this, I really like the idea of a human computer centaur. So a centaur, what I know is it's a mythical creature, which is like half human and like half horse, right? So I like to imagine this as a like analogy. So like while a human can only compute like I can only compute like multiplication of 2-digit numbers, but like with computers, I can go much faster in like computation. And also, I like the human-computer interaction direction. So like drawing sofa on a board can only give you like one picture, but like by iterating through many different like shapes in many different ways using like applications, you can search space intuitively. And so to me, like it enhances your like how do I say perception if you really like find the right spot. So that was how I solved the moving sofa problem. But then the AI comes into picture. So far, I had to program like the right thing for me. Like I had to design all the like interfaces and like I had to come up with the ideas by myself, and then like I told the computer what to do. But then computer started to think on itself. So like the machines start to become like thinking machines. And I told you that I aspired to solve an Erdős problem one day. Actually, Google's Aletheia system, I think it's a Greek, Greek word for wisdom. Their like LLM AI system solved like a bunch of Erdős problems. And this is one of my favorite. Given this vastly this sequence vastly converges to 0, can you show that this infinite sequence is always irrational? And what I can see that this the solution to this problem was kind of, how do I say, people could have solved it if they tried really hard, kind of thing. But like me as an individual mathematician, I think it would have taken me at least like a month or two at least to like grasp all the existing ideas and like train them myself and like come up with the solution. But like the AI goes like, shoo. So like it was a little bit sad personally for me, but also exciting. I also tested some of the combinatorics problems that I liked, which I couldn't solve in like a day. So I have this like a fun little problem. The actual statement, yeah, maybe I don't want to like talk about it here, but you can, I don't know, copy it and like solve it by your own there. So I have this like simple, elegant problem that I liked. I would have really loved it as a middle school student. I feed it into Google DeepThink, and then after like an hour of baking, it spits out the perfect solution, clean cut. So given this, since my main interest was in like a hard Olympiad-like problems with like a node theory, I was like, I should be really aware of this. Like, should I join the and collaborate AI, or like will AI take my job? Like, I'm still like thinking over that. So I'll be happy to discuss that with you. And this is my in progress search on this. And the AI frontier goes it's a moving target too, right? So this is what I found so far, the rest of the talk. So I experimented with AI and realized that it could solve hard problems. Meanwhile, a year, starting from a year ago, there's this student called Jiwon Kim who's working, who's an undergraduate student in KIAS, second year. He's brilliant. Him and I embarked on a mission to solve this problem, solve this conjecture of Soifer, and get $50 from him. He bet $50 on this problem. So the problem goes can you So you have this regular hexagon of side 1, and the task is to cover them with equilateral triangles of sides if you cover with equilateral triangles of side exactly 1, then you can fit it with like 6 like triangles, right? But what will happen if you have to cover with triangles of side less than 1? Like, what will be the minimum number that you need to have to cover this thing? And a covering could go like this. I have something like this here. So because all the sides have like a side length slightly less than 1, like it will kind of like shift a little bit. So I already used like 6 of them, and the rest you have a bunch of hole. And his conjecture was that to fill out the rest of the hole, you need at least like 2 more triangles to cover them. And it's still open. And while people theoretically know that it's like a computer with finite time, but like that finite time is like bazillion years. And what we want is an elegant proof. So we embarked on this mission. And we came up with this strategy. Instead of looking at the, like, how do I say, the two-dimensional interaction between different like triangles is a bit harder to understand. So we try to reduce the problem to covering this like skeleton that we call of a hexagon. So a skeleton is the union of the boundary of the hexagon and the 3 main diagonals. So it's like one-dimensional. And we thought that like 7 triangles are not sufficient to cover this one. And you can already see that like this like conjecture where every epsilon equals the triangles of side S equals 1 minus epsilon. Here what I did was to just fix the side length equal to 1 minus epsilon. It's a strengthening of Soifer's conjecture. So we did this because one of the reasons was that we also wanted to do computer experiment. And for that, like one-dimensional shape is much easier to like compute. So a strategy was this. So let's say that you have this like skeleton. An idea is to sprinkle certain like weights of totaling up to like a slightly more than 7. So like here you have a bunch of dots, basically each of certain number called weight. And the total goes to like 7.03. And what we do was to use linear programming to make sure that each triangle can only cover at most like 1 of the weight. So like if you use only 7 of them, because the total is like more than 7, you will like lose 0.03 of the weight. And that's how the argument goes. And what Jiwon Kim did was to make a C++ software to like find a weight for like a fixed epsilon. And here is a diagram for epsilon equals 0.05, and we push up to epsilon equals 0.03. And it would have taken me like months to actually program, I think. I'm kind of a slow programmer, but on top of that, like, it's something not so easy to like how do I say, debug all these like geometric algorithms. But he used Anthropic's Cloud coding agent to develop it very quickly. I think he did it in like 2 weeks-ish. I was very surprised. But we could not generalize this like weighting. So we tried to plot the weighting for different epsilons and try to interpolate. But we could not generalize up to all like epsilon, positive epsilons. So the project stalled for like months. And then we wanted to try a different approach. So what we did was to solve the original like covering problem. So what I just told you is a relaxation of the covering problem called fractional covering, in which you are allowed to like use a fractional number of like triangles. But here, we wanted to go back to the original covering setup. And an argument that a smart student can come up with is something like this. you have this point, center point, and 6 vertices. All these 7 points have distance at least 1. And if you were to cover this thing with triangles of size strictly less than 1, it can only cover one of those 7 points. So if you were to use 7 of them, it has to cover this one, that one, that one, that one, that one. So like you know that each of the triangles should contain the center or the like 6 vertices. Okay, so this is what we know. And we have this symmetry. This point, this point, this point, they all have like a degree 3, like lines emanating out of the vertices. So like what we wanted to do was to look at like this triangle and like see how far a triangle could cover. So we defined like the admissible set as basically like how far can a vertex covering like a triangle can reach. And graphically it looks like this. So we parameterize them with A, B, and C. And this is the graph, A, B, and C. And the set itself is interesting. Like, it kind of pops out as you have A plus B slightly larger than 1. Like, if A plus B is slightly larger than 1, C goes from like can go from like a number very close to 1, then drops out and suddenly drops down to something smaller than 0.5. So that was kind of the phenomenon that we were like keeping an eye on as we tried to attack the problem. Then this time AI actually helped us. So like this set is basically called a what is it called? It's not algebraic. Semi-algebraic set. Am I right? Like all these like real subsets of like r to the power of n that can be described by polynomial inequalities and equalities. So it should be a semi-simple set, semi-algebraic set. But a human, like it would be very daunting for us humans to come up with the right polynomial set. And like we asked ChatGPT, and it thought for like 70 minutes, and then came up with the right proof and the right polynomials. So we outsourced the like the actual computation, and it could think for itself. Yes. Oh, sure.
Yeah, so as soon as you have that, you can only cover 1 point from the triangle that's at 1.
Yeah.
Why isn't the proof there?
I see. Like the task is to show that you can't cover with 7 triangles. Yeah, yeah. Like, oh yeah, so like it's a good thing to like how do I say, like reiterate, like we can do it with 8. 6 is the lower bound. Like 6 is impossible, so the answer should be 7 or 8, and like we want to push it to 7. So like we came up with the right formula for this admissible set. And then we came up with a like specific strategy. I will go through the actual strategy in the next slide, so you don't need to read all of them. But we came up with this strategy of fixing the triangle in the middle and trying to wrap around the triangle with admissible sets and show that you can like go back to the beginning and like have everything covered. And Jineon Kim actually showed that this strategy succeeds for important subcases, so we believe that it should be true. And then I built an app again with OpenAI Codex to like actually have that in our hand and like see which are the like bottleneck cases, which portions. So do I have the exact equality and should be careful in the argument, etc. So this is the website that I developed. So here I am fixing the middle triangle. I can rotate it. I can also make the center rotation move and like rotate it like that. And the idea is that you start with this point and cover this portion of admissible set. And for the next portion, I covered like this vertex and this like admissible set. You go all the way and like come back here. And this is kind of the greedy strategy, right? if you do this greedy strategy, like you have this portion left in the covering. So like as I like move this point, it's like you will always end up like to the point or like something like a little bit backwards from that. So like you always miss some portion. And from here, like it's like it goes like this. Like how can I come up with a proof strategy? So like basically this whole graph on the right side is like a composition of like all the like how do I say, chains of like locations of A coming from like rotating. So like this is the initial input, then you go as far as you can, then this is the next output, which enters as input again to this vertex, and you have this as output. So like you compose this function with that function, etc. And then the task is to show that you end up with some function that is larger than identity, larger than or equal to identity. So like I tried experimenting with this. So for example, an evil case for this argument is where I have some dip like this. So like basically I want the whole composition to be slightly larger than or equal to the identity function. But here, I drew the function for only this edge, and it's like dips down much below the, x equals y. So I need to somehow compensate that with some other things. So how about I compose this one? This one is a little bit useless. Like if I compose this one and that one, then like the composition is still less than or equal to identity. And here, I combine those two, and those two seem to like beat this line. So like this is kind of the like exploration that I do. So as I like play around this like thing and come up with the right strategy, I realize that this is actually the evil case where I have like some edge very close to vertex. So I played around. And can you actually see something? On the right side, let me remove the yellow part. This is the whole composition. What I wanted to show was that the whole composition should be larger than or equal to identity. But actually, you can see this little dip here. So what does that mean? For this middle triangle, I do the whole wrap, then I cover slightly larger than the boundary. So after doing this exploration, what I realized was that actually we can cover the skeleton with triangles slightly less than 1 inside. And I extracted the coordinates of the triangles from the software, again using codecs. And then we realized that 7 equal triangles of side 0.999 can actually cover the whole thing. So this strategy you have to abandon. So this is the story so far on this problem. Like this happened like 3 days ago-ish. And so far, I still think we human AI Centaur thing is a little bit ahead of for this problem than pure AIs. I asked both ChatGPT Pro and Gemini DeepThink on can you actually cover the skeleton with triangles of side slightly less than 1, and they either run into error, like after long hours of thinking, or they try to prove which is the wrong direction. So for now, for this particular problem, I think we are a little bit ahead, but we will see what will happen in future. And knowing that this strategy won't work is an advance, right? And for that, we already got the help from AI, like programming and exploring, etc. So like, I like this saying, if you can beat them, join them. I got to know this phrasing from a Queen song. There's this rock band called Queen. They have the song title like that. And so yeah, so I can't beat AI. So I'm trying to use AI as much as I can in this journey. So what I did was to run a custom agent loop. An agent loop is simple. You just like ask LLM to do thing, like come up with new ideas on this problem, and they come up with new ideas. I just feed them as the prompt again. You go just like multiple rounds of that, and people succeeded with what is it? So there was this combinatorics problem by Donald Knuth. He asked if a certain graph had a certain object called Hamiltonian path, and people did agent loops on it, and they could find the right combinatorial structure by themselves. So I tried to mimic that using the same prompt I copied here and there, I ran my own codex agent, and well, I don't know, I kind of have mixed feeling. They did not manage to find a covering yet, but they could observe all these observations that I made, in the previous slides. You have 7 points, you have to look at admissible sets, and there's this a jump phenomenon on C as long as you have A plus B larger than 1. So we'll see. So this is my journey so far, and I hope it's inspiring to you somehow. Thank you.